To finally demonstrate an important application of the interaction between electric and magnetic fields, we built a simple electric motor. Electric motors convert electrical energy into mechanical energy. This is achieved by applying principles of electromagnetism, creating repulsive magnetic forces that translate into mechanical movement. The main parts of a motor are
a stator, which is usually a stationary magnet, a rotor, a coil of wire mounted on a spinning axis, a commutator, a component that interrupts the constant flux of current through the coil, switching the direction in which the current flows every half a turn, and a power source that provides a flow of current to the system.
For the development of it, we made a coil with insulated copper wire and sanded each end of it in a way that the insulating coating was only removed from opposing sides of the wire. The enameled areas of the wire work as a commutator. Next, the coil was placed over neodymium magnets across a couple of aluminum supports. Then, we supplied direct current to the coil with a 9-volt battery. With a small initial force applied to the rotor, the rotational motion was able to initiate.
According to Ampere's law, a current density flowing through a conductor creates a magnetic field around it. This principle is applied in the loops of wire that make up the coil, creating an intensified magnetic field each time the current flows through them. If a time-varying current is applied, a time-varying magnetic field is created.
It is important to bear in mind that when two magnetic fields are brought closer by opposite poles, an attraction force is created, whereas a repulsion force is created if they are brought together by equal poles. This repulsion results in a mechanical movement, created when the stationary magnetic field of the stator is brought closer to the time-varying magnetic field of the rotor. Time dependence of the magnetic field of the rotor is created with the commutator that interrupts the constant flux of current and inverts the direction of the flow every half a turn, allowing a constant rotational motion created by two forces with opposite directions on each end of the coil, creating a torque that causes it to spin.
The behavior of the coil's motion due to the magnetic field and current is cleared by applying Fleming's left-hand rule, which uses the thumb, first, and second fingers at 90 degrees to one another. For this rule, the thumb stands for the force applied to the coil, and hence determines the direction of the wire's motion. The first finger represents the direction of the magnetic field, and the second finger the direction of the current.
When the coil is in a vertical position, as shown in the figure, current is able to flow since the commutator is not in contact with the coil. Therefore, opposite forces on each end of the coil are present in order for the wire to spin. The magnetic field is always pointing from the north to the south pole, and the direction of the current is opposite in each end. On the other hand, when the coil is in a horizontal position, the insulating coating acts as the commutator, interrupting the flux of current.
Consequently, in this position there is not current nor force present in the conductor. However, due to the inertia of the coil, rotational movement continues. We can observe that the wire's end coming close to the south pole experiences a mechanical force out of the screen, whereas a force into the screen is experienced by the conductor's end approaching the north pole.
When the coil completes a turn ending in the initial position, the whole mechanism starts again, keeping a constant rotational movement, hence converting the electric energy into mechanical energy through electromagnetism.